Good afternoon, everyone. Welcome to today's session. My name is Joe Ghaffari, and I'm a member of the Spark program by CANSSI Ontario. The CAST series is dedicated to spotlighting groundbreaking research in statistical sciences, both applied and theoretical, from across Canada and around the globe. The primary goal is to provide a platform where participants can engage directly with leading experts to deepen their collective knowledge of statistical research. CANSSI Ontario is committed to strengthening research and training in the field by developing programs that foster interdisciplinary research and multidisciplinary collaborations. It is now my honor to introduce our speaker for today, Dr. Radu. Dr. Radu is a professor of statistical sciences at the University of Toronto. After studying mathematics at the University of Bucharest, he earned his PhD from the University of Chicago in 2001. His research focuses on computational methods, more precisely Markov chain Monte Carlo, copula models, and statistical genetics. Beyond his research, Professor Radu is a vital voice in the academic community, contributing editor and associate editor for several prestigious journals. His contributions has been recognized with several accolades, and he is a fellow of both the Institute of Mathematical Statistics and the American Statistical Association, a faculty affiliate of the Vector Institute, and an elected member of the International Statistical Institute. Kindly to join me in welcoming Dr. Radu. So, Doctor, the stage is yours.
Thank you for the introduction. Thank you for being here. Let me start by sharing my screen. Okay, so today I want to talk about two projects that are related by the fact that they both use copulas and they both use copulas in both of these cases are used to model latent variable structures, and you'll see how. I will probably, it's hard to take questions on Zoom, so I will pause from time to time and ask if there are questions, and hopefully that will give you the opportunity to ask questions before the end of the talk. Okay, so the first project I want to talk about is something that has been published already and was developed with my former PhD student, Robert Zimmerman, and my colleague, Vianney Lewis Barajas. And it has to do with hidden Markov models. Okay. I don't know why the advancement is so slow. Okay. So for the students in the room who may not be very familiar with the hidden Markov model, we're looking at longitudinal data, essentially, YT. So you see there the Ys are observed. These are the observed random variables or random vectors in a second. And the behavior of these, the distributions for these observable changes in time, okay? And the model assumes that there is an underlying latent process, which is not observed, xt, which is discrete. It has the state of space, the state space is discrete, and it's a Markov chain, okay? And essentially, depending on the value of x, you will have a particular density for y. So given that xt is k, you can see here the x with the h component of yt will follow a density f k. K is the state, right? The hidden state. We refer to these values of x as hidden states, and for the h component. And this density will be parametric and will depend on a parameter lambda kh. And this is true for every h between 1 and d and for every t. So as I said, xt is a Markov process with some initial probability mass distribution pi I and transition probabilities gamma ij, the usual notation. If you've seen any book on Markov processes, you'll recognize these concepts. And the inferential aims for HMMs are depend on the application, of course, but typically the chain XT is either partially or completely unobserved. So sometimes we go back and we look at the data, we spend more money and we figure out the hidden state for some of the observations, and then based on that we can infer the other observations if they were in some of those states or others. So it's also true that sometimes the hidden states can correspond to a precise variable. We will see in our example, this is actually it has a physical interpretation, but sometimes it could be just something that we postulate. We don't have a proof that such a latent variable, such a latent process exists, but we want to use it to shed some light on a complex phenomenon that changes in time. And such examples abound in psychology, ecology, and so on. So aim one is, for instance, to model the data generating mechanism. We simply want to know how many hidden states there are, how those densities depend on the hidden states, and we try to make some inference about those. Another aim is to decode or classify, predict the XT, the hidden states from the observed data. Just to see some examples, you can see that we saw examples where a triaxial accelerometer, this is a tough word, captures a shark's acceleration with respect to 3 positional axes, depending on the shark's activity: resting, hunting, attacking. In another example, so what we measure acceleration along 3 directions, and depending on, as a function of those, we try to infer whether the shark is resting, is hunting, or is in an attack mode. Sometimes attacking means, unfortunately, attacking humans, and that has nothing to do with hunting or eating. Hospitals repeatedly, for instance, record a patient's vitals post-surgery to understand the state of their recovery. We want to understand if the recovery is going as predicted, is stable, whether there are complications, or whether the recovery is complete. So in other words, that the patient can be released. And in more complex examples, and hidden Markov models are used with various degrees of complexity, additional complexity than what I described in econometrics. And as an example, you can see that stock exchanges, we can keep track of real-time prices for hundreds of stocks within an industry, depending on market condition. So the price of the stock or the evolution of the stock prices can tell us whether the economy is stagnant, growing, shrinking, and so on. This is a very complex model, so we're not looking at something that complex, but I gave this example just to show you that essentially this is a very widely used model, and in general, in these examples, we can see that we don't observe just a single random variable, we observe a vector. So it is essentially, we're looking at a multivariate time series, or if you want, multivariate longitudinal data. So in such situations, we cannot assume that the components of YT are independent. Certainly, they are not independent marginally, because all of these depend on XT, the hidden state at time t. But even so marginally, they are not independent. Marginal, I mean averaging over all the possible XTs. But even conditionally, they may not be independent. And this is something that we have observed, and I will show you an example where that happens. So when we cannot assume independence, it's common to assume that YT follows a multivariate Gaussian distribution, and then we can model the correlation, for instance, the correlation parameter as a function of XT as well. And that's fine, but what happens if some of the marginals are not Gaussian? And how can we actually account for other dependent structures? What if you have non-zero tail dependence? and we believe that your joint distribution is not symmetric. So things like that clearly require a different type of methods, and 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 relevant here, beyond the modeling part, there is also a question about whether there is information about the underlying state that comes from the dependence itself. Okay, so beyond the marginal information about xt, there could be joint information about xt. So after we take all the signal from the marginals. What if there is more left in the data, and how can we take advantage of that? So this is an example that we used in the paper, the occupancy data. So this has to do with the ability to detect whether a room is occupied using sensor data, such as temperature and CO2 levels, without the use of cameras, right? Obviously, if you have a camera, you can figure out if somebody's there or not, but some places don't allow the use of cameras, for instance, in a gym, right? In a change room. So in such a case, you want to be able to tell whether it's occupied or not based on these other measurements. And we used 3 publicly available data sets. And here the observables are three-dimensionals, okay? And and you can see on the left what is left in the dependence after we account for the marginal effect, okay? The information in the marginals about the underlying hidden states. There are only 2 states, hidden states here. Either the room is occupied or unoccupied. And here is the dependence left after we account for the marginal information about whether the room is occupied or unoccupied. So clearly, the 2 dependencies are different. So in this case, you can make an argument, even without doing any math, that there is information in the dependence pattern that should be able to give you more power when you diagnose or decide whether a room is occupied or not. Okay. So there's no secret here. I was pretty open from the beginning. These 2 projects have a common denominator, is the use of copulas. And the copulas are mathematical devices which are used to model dependence between random variables, okay, regardless of their margins. So that's a pretty powerful statement right there. Of course, it comes with a number of complications. So, in my opinion, beyond this model, this classical standard sentence to model dependence, to account for dependence, and so on, but the copulas are also useful for data fusion integration. Okay, so if you have disparate measures about an underlying phenomenon, and you want to understand how all these data can be combined, well, they have a joint distribution. Okay, and if they have a joint distribution, we know, we'll learn in a second, for those who not familiar with it, there is a theorem that says as long as these things you measure are continuous, they will have a joint distribution which is characterized by a particular copula. And so all of a sudden, we can create a joint distribution with marginals that could be widely different, and this will be a coherent joint model for any copula. And there is one that will make the model very useful, is the true copula, of course, which is the one we're trying to estimate or approximate. In other ways, another way to look at copula, how copula serve us as modeling statisticians, you can think of them as unlocking information contained in the dependence part of the distribution. Okay, so this is second order information. The same way variance is a second order information about what's happening in the generative model compared to the mean effect. Okay, so you can think that we can make a pretty strong point that such information can complement the information in the marginal. It's rare that the distribution in the dependence part will be stronger than the information in the marginal, but it's addition could be significant. And the standard, another standard, I started with a standard sentence and end with another standard sentence, is that Copulas extend statistical methods beyond the use of a multivariate Gaussian or student. Because if you think about how many multivariate distributions there are not that many. And certainly once you throw in different marginals, the set becomes quickly empty. So this is the theorem that I mentioned before. It's widely known by now, thanks to the work of a great Quebec school for Copulas, Christian Genet, Jean-Paul Rivet, and so on. But essentially, it says if y1, y2, yd are continuous random variables with cumulative distribution functions f1, fd, there exists a unique copula, which is essentially a distribution function on the unit hypercube, such that the joint distribution function h is going to be the copula, and to which you replace in the first argument the first CDF, and in the last argument the D's CDF. So you can see the name now because this C function links the marginal CDFs and creates the joint CDF. Okay, and when these are continuous, there is this copula is unique. This is a very important fact, and and it's also equally important, we'll see in the second project, that this can be extended to conditional distributions. So in other words, the joint conditional distribution of y1, yd given some random vector x will be similarly equal to a unique copula applied to the marginal conditional for y1 given x and the d's marginal CDF, marginal conditional CDF of yd given x. Okay, and the fact that this bar given x means that the copula itself now is no longer fixed, is no longer a static copula, it's a dynamic copula. Okay, so the copula itself changes with x. For instance, if you choose a parametric copula function, copula model, you will allow the parameter for that copula to change with x. And how it changes with x is something that Elif, who is here online, can tell you a lot about. Okay, so how we're going to use this within the hidden Markov model I presented first, it's pretty straightforward, right? At every time t, we have to model the conditional distribution of yt, the observable vector, given the hidden state is k. Okay, so why don't we model this using the copula formulation? So we are going to say that this distribution is ck, so the copula depends on the hidden state, and you'll have the usual HMM formulations for each component of yt. These elements appear in the standard hidden Markov model formulation, and now this copula will depend on a parameter theta k. The theta k is specific to the hidden state. So if the hidden state is 1, this will depend on theta 1, but if it's in state 3, it could be a different copula and will depend on a different parameter. And these parameters may not be living on the same space, just to clarify that. This is clear that the CK is a d-dimensional parametric copula, sorry, and we repeat some of the elements just to remind everybody that. So in this model, virtually all aspects of the state-dependent distributions are allowed to vary between states. So for a range of dependence, if you want, dependence strengths, we simulate a bivariate time series of length 100 from a two-state hidden Markov model, where you can see that the marginals are both normal. So there is no information in the marginals about the hidden state, but there is strong information in the conditional dependence. And this is a simulation study to show that the 0-1 loss as theta increases. So as you have more information in dependence, you'll tend to make less and less errors in identifying the hidden states. But if you assume independence, you'll not be able to tell anything. Essentially, it's the same as flipping a coin. And that's not a coincidence. We were cheating a little bit here because we set it up so that the marginals are not informative about the hidden state. Okay. So this is the idea. So far, this is the setup. And from now on, we will talk a lot about computation. So the issue with copulas is that they are very powerful, as you can see from the theorem. However, it comes with some important complication, caveats, whatever you want to call them, that makes them less widespread. Their use less widespread than we would like, and one of them is computation. Every neat statistical model which has nice conjugacy in computation, if you're a Bayesian, or it has a nice EM, if you're a frequentist with missing data and so on, will collapse when you introduce a copula. Simply, copula breaks everything. Most copulas. So that's why we have to be careful how we do the estimation and the computation. Maybe I stop here to see if there are any questions. Okay, I don't hear anybody. You can just unmute yourself if you want to ask a question. So I'll go on with the estimation. So here, just to summarize what we know and what we don't know, the data consists in the observed Y1T, and the latent, or the missing, if we want to adopt the terminology of an EM algorithm, it's X1 to T, the latent process. The parameters are the parameters which direct the way Y depends on X. So these are the lambdas marginally. And then you have the copula parameters. And then you have the parameters gamma and pi, which essentially govern the dynamics of the Markov process. So the complete data log likelihood for one trajectory of the copula is given here, and it has to do with the initial value, okay, where the latent chain starts in the state x1, and then the transition for the latent chain, and then you have the contributions for to the log likelihood by the marginal model for yt given the hidden state xt, and then you have the contribution given by the dependent structure, which is modeled with the copula. And this little c is the derivative of the copula function, the capital C, with respect to every one of its arguments. So if we didn't have the copula in there, the estimation would be done for all the parameters except these zetas, would be done using the EM algorithm, which is known as Baum-Welch in this setup. And it's pretty standard by now. Everybody knows how to fit such a model. And with the copula, we still have to do the E step, in which we compute the expected value of the log complete data log likelihood. And it's a conditional expectation. We condition on the current guess about the parameter value and on the observed data. So if you look under the hood, these E-step elements, this E-step will depend on computing some conditional probabilities for one is the marginal of xt being k, given the data we observed and the parameter values we have in the current iteration, and the joint distribution of xt minus 1 and xt, given the observed data and the guess about the current value of the parameters. And this step is okay. Nothing special there. However, in the M step, the resulting complete data log likelihood has to be maximized with respect to all the parameters, as you well know, in simultaneously. So that's the tricky part. This simultaneously part is the tricky part. So the unfortunately numerical methods for this model are unstable, and in fact a lot of times they don't converge. So the EM, where we just plug in blindly the M step using some numerical optimization algorithms or gradient-based methods, fail. So what to do? And this is where we went back and looked at what do people do when we estimate copulas, right? So when you estimate copulas, you can have the joint maximum likelihood estimation, or you can do a two-step, you can adopt a two-step approach, okay? So the two-step approach is called inference functions for margins, and it was developed by Harry Zhou and collaborator Xu in 1996. And the idea is to first, so this has nothing to do with the current model, okay? This is in general. We first estimate each marginal parameter, so the parameter that governs the marginal distributions, okay? So this lambda h, and we replace them, we find lambda h hat, we plug them in, and then we estimate theta, assuming that the marginals are fixed at with parameters lambda 1 hat and lambda d hat. So we assume that these are known now, and we just estimate theta separately. And this actually simplifies a lot the computation. And there is it's still consistent estimator. We didn't show that, obviously. Joe showed that. And asymptotically normal, but it has a little loss in efficiency, okay? So what we want to do is essentially we want to do the same in this setup, right? So within the EM algorithm, we want to, in the M step, we want to apply an inference functions for margin approach. And because I want to have some time to talk about other things, I'll probably skip this. The idea is exactly what I said. We first estimate the parameters, and then we estimate the copula. The fly in the ointment, so to speak, is that these expected inference for functions for marginals algorithm, these creatures we just produced, is not a generalized EM algorithm. In other words, the likelihood is not guaranteed to increase after each iteration. And this is where this was essentially the bulk of the work here to prove that this particular approach is still a valid approach in the sense that the algorithm will converge to a local or global maximum, just like the EM. The EM has no guarantees they will converge to the global maximum. And the estimator we produce numerically is consistent and asymptotically normal, okay? And the way we did this is by adapting proofs produced by Elashoff and Ryan, and using the asymptotic theorem estimators for HMMs produced by Jensen. Okay. So how do we run this? We assume in this particular application, occupancy and the room is either occupied or free. K is no, it's only two, right? There are only two states. So we assume here that K is known. If K is not known in your data, you can create an initial clustering algorithm based on either some empirical methods, or you can use even copulas, like Sahin and Chado did in their paper, and come up with a value K. In the numerical experiments, we also considered K-means algorithm for clustering, pretending that we don't know the true value of K, and this also seems to work okay. Now, of course, yes, Michael, yes.
Yeah, so you're doing a Gaussian of a Gaussian. In other words, are we in your theorems, assuming the y's are Gaussian, and now you're putting a Gaussian copula on top of those? Is that what we're doing here?
At the beginning, as a startup, this is how we we initialize the algorithm. Because in order to initialization.
But when you do your theorems, are the theorems dependent on the y's being normal or not?
No.
Okay,
No.
that's what I'm getting at. That's what I'm getting at here. Okay.
Yeah. Sorry. So this slide is this initial parameters values for the copulas is just for initial parameter values. This is how we start the algorithm. Yeah. But the theorem, no, the theorem is general, has nothing to do with the Gaussian.
Great, thanks.
Okay. Thank you for the question. And right, so indeed, the question was right. I mean, it raised a good point. If the marginals are Gaussian and you feed a Gaussian copula, you're essentially feeding a multivariate Gaussian. So it's simple to initialize your algorithm. That's why we use it. But it's clearly not something you want to use in general, because the whole reason we developed this method is to not use multivariate Gaussians. All right, so does this work? First example, we tried 2, 5, and 10 dimensions for the multivariate response. We had a two-state HMM in this particular example. One is Frank, one is Clayton, and we used the parameters using both approaches. I mean, what we mean by both approaches, we tried EM without any modification, just vanilla EM, and in which the optimization part, the M step, was attempted with this gradient descent method, and this fails as soon as D is greater than 3. So these are sort of some of the results. So this is the volume of the sample size, if you want. The time series has length 100, 1000, or 5000, and you have D equal 2, 5, and 10. And even with D equal 2 at 5000 observations, the algorithm cannot be finalized, because I think it runs out of memory. And also you can see that even with 1000, when D is 5, this is the error between two consecutive iterations of the parameter, it explodes. Okay, so numerical error creep in and things blow up. And in contrast, the algorithm we propose is stable, and probably we had to run it longer to reduce this epsilon, but we don't see any signs of errors getting out of control. Okay, this is another experiment where we have student marginals and 4 states. In each state, you have a different copula, and we try to recover the parameters. So now, of course, when you fit a model like this, you don't know the true values of the copula. So what happens? We need to identify from a set of copulas. We hope that one of them will approximate the true underlying dependence. And there is no perfect scenario here. We didn't go on a non-parametric route. We didn't look into empirical copula approaches and so on. That would be interesting too. But here, I think we wanted to also try to explain a little bit of the dependence using one of the existing families. And we tried, I think, I don't know, Robert tried 12 copula families and for the real data example. Okay, so let me move my windows here. Okay, so you can see the stopping rule tolerance. So let me refresh the number of iterations taken by the algorithm we propose before stopping, using tolerances of 0.01, 10 to minus 3, 10 to minus 4, 10 to minus 5. And you also have classification accuracy of initial k-means clustering and or local decoding with parameter estimates provided by the EIFM algorithm. So the local decoding leads to better results. And whether you think these differences are significant or not, that depends on the application and depends on the stakes that are in the play. It's interesting, and we still don't quite understand why we see this non-monotone pattern here between the sample size and the number of steps required to reach a particular tolerance. It could be that we haven't done enough replicates, or it's just it's an interesting phenomenon. We still don't know. I'm happy to hear suggestions if you think there's something here. It's one of those mysteries. Okay. Maybe there's a more complex model that one could look at in the paper. I want to look a little bit at data. So the occupancy data, we have three classifiers. One is the k-means clustering. One is based on independence copulas within hidden Markov models, so we ignore the dependence. And one is, after looking at, I believe 12 or 15 copula families, we set up on these two families for state 1 and state 2. And we had the error in the training data, or the accuracy in the training data, and then we had the accuracy in the test data. And you see modest gains, simply because in this case, the marginals are also very informative. So after you squeeze the information about the state, the hidden state, from the marginals, there's only so much that is left in the dependence to further elucidate what's happening in that room. But certainly, we hope that in other examples, this could be make a bigger difference. Okay, so this is the end of the first presentation for the first project. I'm happy to take questions, if any. Right, so the second model, I won't go until the end, but the second model is in collaboration with Robert, who is still working on this while also working in industry. So this is going to develop a lot less quickly. But let's see what it's about. First of all, what kind of latent variable model we are talking about here? So this is a situation. This particular latent variable model has to do with a situation in which the variable of interest, W, is impossible to measure directly. And there are countless examples like that. For instance, state of the economy. I alluded to that earlier when we look at stocks, but it could be many other things that you can throw into the mix to inform about the state of the economy. How much renovation people do on their houses, and so on and so forth. Traffic in a city. There are many ways in which you can measure this. State of your health. What does that mean? It's a latent variable. It could mean many things, and it's informed by many measurements, not just your blood pressure, but also your sugar levels, when you do your analysis, and or state of a complex disease. So we looked in the previous work at diabetes, who can manifest itself later in life in various complications, and understanding the state of a disease, for like diabetes, could also help you identify the genes that are responsible for accelerating or slowing down the evolution of the disease. So this could be also what I mean is that this could be just an intermediate step in the final analysis or the final goal of your study, but it's still an important one. So instead of the variable of interest W, one measures a number of components, K components, which you can think of as surrogates of W, and each provide partial information about W. So for the state of your health, so remember all these tests, right? You'll have a test for your sugar levels, for your kidneys, for your heart, for your lungs. And you can think of all of those tests being a component in this vector. And together, they tell you something about your health. And so they are all correlated to some extent. And they all inform you about this W that you cannot directly measure. And you also have covariate information in this particular project. We assume that. And this could be your age, could be the stress of your profession, and so on. And we often are interested in the explanatory power of X for W. So in this particular project, we use we settle on an example where the two responses, one is discrete and one is continuous, and this is a much more complex situation than if you have both responses continuous, or you have a vector of continuous surrogates and you surrogate variables, and you try to understand from them the latent variable. So the latent variable in this case is we're looking at cardiotocography, which is a medical procedure that monitors the fetal heart rate. The latent variable is the fetus underlying state of health during birth, W. And what we're measuring during the birth, which can be hours, fortunately, is a bivariate vector, Q, where Q is discrete, is the number of peaks. This is defined as acceleration followed by deceleration of heartbeats for the signal recorded by the CTG. And Y is the log of mean short beat-to-beat variability. So this is a continuous random variable and is obtained by measuring the time between successive R waves. This is a little getting very complicated. And Robert talked to some obstetricians who provided some information about these things. It's certainly above my pay grade. The covariates are fetal movement, which is also measured, and uterine contraction, which are both continuous variable monitored during birth. So this is just the sort of a running example, but the ideas are pretty general. Okay, so in this particular, for instance, for this particular data, we could think of a canonical latent variable model as one in which we assume that given the latent variable, the yi and the qi are independent, and the yi given wi has some sort of, it follows a Gaussian, so it's a regression, a linear regression model, where the latent variable predicts this beat-to-beat variability. And the associated parameters are mu c and lambda c, and it has a variance sigma squared. Similarly, the discrete random variable qi depends on wi, and it's in through the Poisson regression. And finally, the wi depends on the covariates. There are two of them here through this linear regression. And you know, at the beginning when we started working this problem, I thought, this is interesting. So they assume independence. Why don't we assume the whole distribution? And this is going to be the next step, right? We're going to model the joint distribution as a function of wi. And how do we integrate that into the model is through the copula. But if you think about it, this also specifies the joint distribution for yi and qi. Because if you integrate out wi, you'll get a joint distribution for these two, yi and qi. And this joint distribution will have a marginal that is continuous and a marginal that is discrete. However, I have no idea what that is, and probably is not available in closed form. And it would be difficult for me to tell you something about the tail dependence, extreme events, and so on. So you can think of the and that joint distribution is completely dictated by these marginal and by these conditionals and this marginal, right? Because we will get the joint distribution by looking at a trivariate and integrating out Wi, and we end up with a formula that is not available in closed form, and but it's also not something that has flexibility in it, right? Because unless we change these elements. So here, what I'm trying to say is that we define a joint distribution between yi and qi, but we have less control and less flexibility than if we use a more general model. So the more general model, as I said, is, okay, conditional on wi, let's model jointly. We know that there is a joint model between yi and qi. And it's going to be a copula. And which now the parameter will depend on it's going to be a conditional copula, essentially, because we're modeling a conditional distribution. If you remember at the beginning of the talk, when I introduced Clark's theorem for copulas, I said the same holds for conditional distributions. And that's indeed the case here. Now, before you even ask me, I'll tell you that here, one of the marginals is discrete. And you'll tell me, well, you told us that copula is unique only if the marginal is continuous. And that's true. So this, if we adopt a non-parametric approach for this copula, indeed, we will not have a single estimator. However, in parametric estimators for copulas, the MLE for the copula parameter is well defined. There is no unidentified. It's not unidentifiable. Therefore, the copula is perfect. Is well defined. So there is this delicate difference between parametric and non-parametric models. Okay, so the whole joint distribution of y and q now is varying with w, not just the marginals. And this is another way to create a more flexible set of joint distributions between yi and qi, related to my previous comment. You can also think that the copula captures the residual dependence on w after the marginal effects have been accounted for. Okay, so and the original model, the model that we're generalizing here, is obtained when the copula is the independence copula, right? So clearly, that example, the classical latent variable model that people usually tend to use, is obtained as a particular case of this one. And a question is, why the conditional copula? Why do we need a conditional copula in this case? Why not use a stationary or a fixed copula? After we take out the effect of the marginals on wi, how much more can it be, and why does it have to depend on wi? Well, let's look at a simpler example. Let's assume now that we have integrated out the wi. So you'll have essentially yi and qi in that example. Here I will assume that I have y1 and y2. I just have two random variables. They are dependent. They depend on the copula, on the covariate x through the mean function, right? So y1 is going to be normal with mean f1 of x and variance sigma 1, and y2 will be normal with mean f2 of x and variance sigma 2. And I'll choose some values for this f1 and f2, okay? I will also assume that the variances are known, 0.2, that the covariates, there are two of them, x1 and x2, are independent of each other. And I will assume that the dependence between these y1 and y2, the dependence between them is fixed, okay? So the copula here, I think it's a Gaussian copula, and it's going to be, or no, a Clayton copula, sorry, and the parameter is going to be 0.71, regardless of the value of x. So x is x1, x2, it doesn't matter what they are, the dependence is the same. So now I'm going to say, suppose I don't measure x2. I simply don't measure x2 because I don't have x. And I will construct my inference only on x1. And I will estimate the copula parameter as a function of x1 after I model the marginals. Now, the marginals, of course, will not be able to, I will have non-parametric estimates of the first mean, non-parametric estimate of the second mean, but only as functions of x1, because I don't have x2, right? And I will also assume, I will not assume that the copula has a constant parameter. I will allow dynamic evolution as a function of x1. So the question is, and I'll give 10 seconds for you to take this model in and to think, if I plot now this estimate, theta hat of x1, do you think it will be constant or not? Right? So the true copula is fixed. The covariates are independent of each other. In theory, we kind of expect this to lead to a fixed copula in x1. And that's not true. Okay? We can prove when we did in this paper with my former student Evgeny Levy, we proved that this is in fact a mathematical result, and it has to do with the fact that these two functions are not additive. I mean, one is not, and that ruins the intuition, breaks the intuition. But it's very important because in general, going back to our model, we're not sure that we have measured all the covariates that have an effect on the response, especially in a situation like a birth, where it could be many hidden variables there, not many, but it could be one or two covariates that are important and we don't measure them. And in that case, we kind of are cautious and work under the assumption that if a covariate that should be in the model is not there and the effects are not linear, then the conditional copula is a safer bet and will produce better inference. Okay, so I think I'm approaching the end. There is another trick that I want to mention before I move forward, is that we can introduce, in order not to work with discrete random variables in the copula, we can introduce a latent variable, continuous one, a z, so that the q, the discrete one, is obtained by thresholding z, right? And so z is essentially like a latent variable, or it's a data augmentation procedure, and will simplify the computation. And these ideas have been used before by Smith and Khaled, and we have a paper where we use this for logistic regression. Same idea, we just augment the data to allow us to have a little bit more. It can sometimes simplify this is a Bayesian approach. So the conditional distributions that we use for the MCMC can be easier to manipulate. Okay, so so this is the model. Now we have the latent variable. We have the augmented data, the augmented variable that helps us deal with this Q. Zi, because Qi is thresholded from Zi, so these are in a monotone relationship. So therefore, the copula between Zi and Yi, given Wi, so this is the new random variable, is going to be the same as the copula between Qi and Yi. Because monotone transformation leave the copula invariant, and Qi is obtained from Zi using this type of thresholding procedure, as I mentioned before. In general, you don't want to have restrictions on the copula parameter. This theta is assumed. Different copulas introduce different restrictions on their parameters. So you want to create a transformation that moves them to the real line. And my final words will be about the copula criteria. copula selection criteria and the model selection in this context where you have dependence. So the WAIC is a Bayesian counterpart to AIC and is defined in terms of quantities that have to do with the posterior distribution and expectations with respect to the posterior distribution of the parameters and the latent variables. And they have been introduced by, yes, Michael.
Yeah, all of a sudden I'm thinking related to the BIC, the Bayesian information criteria. Yeah.
Yeah, the BIC could also be used, but the Bayesian analysis nowadays recommend WIC because they find that the penalty is more realistic for complex models, complex Bayesian models than the BIC. There are some papers by Andrew Gelman, Aki Vektari. This is not something we developed. We took it for granted, but certainly we looked at AIC and BIC and WIC, and it seems to produce better results in this setup. And the analysis has been. I'll be happy to send you some papers if you want. And what our development, if you want, is here is in the context of copula, we are interested in conditional distributions because where is the copula going to kick in? It's going to kick in when you try to predict one variable given the other, right? That's going to matter. That's where the dependent structure matters. So if you want to identify the model that gives you the best, or in this case, the copula structure that gives you the best prediction of one variable given the other, you need to consider not joint prediction, but rather conditional probabilities of getting yi right given that you have qi and getting qi right given that you have yi. So these are two conditional WIC criteria that we look at, and they are not symmetrical. And if you think about it, in this case, it's pretty clear. Imagine qi is binary. I'm taking the Poisson and I push it to an extreme. It's a binary random variable. How much information do you expect to have in qi about yi? Very little, right? Because you are taking a continuous, perhaps a latent continuous random variable, and you threshold it. In fact, this is how we define the probit models and so on. And there's a lot of information loss. So this will be very poor information, and therefore the copula will be very ambiguous. This part of the WAC will tell you very little about the copula. However, on the other hand, having the continuous random variable, if there is dependence here, you should be able to do very well on predicting qi if you have the correct dependent structure. So what here is interesting is that this, in our particular example, the conditional WAC where you predict q given y is going to give you a better information about the true copula or the best copula than the other one. Okay, so here, for instance, we look at an average, but I don't think that's right. Okay, so this is something that we're currently looking at, how to weigh these two properly when the information in one variable for the other is asymmetric. And I think that's an interesting question. And sorry, yeah. Michael?
Oh, I must still have had my hand up. I'm sorry. I'll lower it.
Oh, okay, no worries.
I don't see where it is, but
that's okay, don't worry about it. And then okay, so finally you can see in the simulation experiment that this is exactly what happens. When we try to predict y from q, we end up with the independent copula as being the right one, while when predict q given y, we end up with the correct copula, which in the generating copula, which in this particular simulation scenario was the Gaussian. And okay, so that was the final notes. There are some plots here about computation, but I think I'm running out of time, so I'm gonna stop here, leave you with these parting thoughts. I think copulas offer a way to bypass the scarcity of available joint distributions. They allow the integration of multiple dependent sources of information, data, via coherent joint modeling. They can be used, these joint models can be used for prediction or imputation of an expensive variable given values for cheaper ones. Think COVID testing, where you had the quick ones and then you had the long ones. It would be nice if people could use the cheap ones to shorten or give you more freedom to move while you wait for the one that takes 2 days. So far, the copulas have been used to further empower multivariate regression, time series, HMMs, latent variable models, etc. And the question is, how far can we and how to use this intelligently? There are computational challenges, especially in higher dimensions. In higher dimensions, there are also modeling challenges. And the papers that you may be interested in are here. Thank you. Happy to take questions. Elif has her hand up. Yes, Elif.
Yeah, hi Radu. I'll just turn on my video as well.
Okay.
Nice. Well, great talk. Thank you very much for sharing your recent research. I have like two related and broad questions. So one of them is when you kind of consider latent variables with copulas, a natural way of thinking of those is the factor copula models, where you kind of have the factor structure. So how is it related to the factor copulas that Harry Joe and like Pavel Krupski kind of worked on?
Yeah. So yeah, I think they're not that far. But here, I think the aim is to understand this joint distribution of of the um, of the observable given the latent, and everything, all the byproducts of that joint modeling are useful and can be of interest to applications. So I think factor copula models will be it's a little bit less how to call this there's less synthesis aim in there, so I would say that's probably the difference.
Yeah, it is mainly used for dimension reduction
Yeah.
purposes. But like together with the, I think your main consideration here was the covariate effects on top of the,
On W, yeah.
yeah. And in terms of the first part of the talk, so you mentioned in the motivation the stock prices, let's say the stock exchange. So when would one should consider the hidden Markov model with the copulas as opposed to just like, let's say, analyzing jointly the multivariate time series? Like, so what
Yeah.
would be the main benefit there to consider the hidden Markov model structure?
Right. So I think if you have a non-station, you suspect non-stationarity, for instance, that would make it difficult to set up a general time series model. You can also, yeah, I would say that's probably the main reason. It's also possible that you'll have. So I'm not an expert in time series, but from I took a class long time ago, and what I remember is that there is only, I mean, if you want to have nice models, you assume sort of Gaussian errors and things like that, right? And for instance, I don't know how they would proceed if some of the time series are discrete, some of the time series measure discrete random variables, some others measure continuous random variables. And I can also think of situations where you look at not only stocks, but you're looking at other measure of like number of unemployed people, things like that. That also tells you something about the economy, and they're measured on a different scale or a different type of variables. So if you want to integrate all of them in a joint model, I think classical time series, multivariate time series model may have trouble. But having said that, if you give me or you yourself, you give yourself 100-dimensional vectors and you try to set up a copula model for that, I don't know. It's also very difficult, right? Because although conceptually you can do Vine copula decomposition and you can work with some assumptions, but fitting such a model requires enormous amount of data, and you have to make choices at every step. All of those conditional copulas in the Vine decomposition have to be chosen, have to be selected, have to be justified. So I'm afraid there's no easy answer here.
Thank you.
Yeah, thanks for the questions.
If there's no more question, I can ask maybe one more.
Sure.
So there, I guess like the copula selection was a bit problematic, like in a way that you have the hidden states and you're kind of doing it in like not just two-stage, but like the maximization step was also divided into two, and you also had the copula selection on top of that, right?
No, we do the copula. So we have this algorithm to fit for any copula, and you run it for different
Parallel,
copulas.
and then
Yeah.
at the end you do the selection of the best model.
Yeah.
Okay. So your question about the simulation results, the computational results, the number of steps like till error, I guess you had a question about like you didn't see why the pattern was not obvious.
Oh, yeah, yeah. Let me see if I can find it here. Right.
So,
No,
but
here.
did you have replications here or like, or is it what just based on one?
No, I think, yeah, that's a good question. I can't remember right now, but I believe everything was based on replication, but maybe 10 replications or something, because
Okay.
it takes a while. So it's possible that if we increase the number of replications, we see things stabilize in the proper way. Yeah, um, but it's always nice to have a little mystery. I remember Christian always has something mysterious to tell you. Like, if anybody can tell me what's going on, it's going to be good. Yeah.
Yeah.
All I can say is I wish I had the time to help you. So there are parallels with my thesis research. My thesis was in 1986, and at the time, I was following Christian Genet, or I'd seen him a few times when he was developing his copula papers, and I could see the parallels. But since then, I've been working in applications, and the last 20 years in industry. So, as you alluded to during the talk for your colleague Zimmerman, it's hard to get time to do independent research when you're in industry. But I'm it's very inspiring, this talk, and I'd like to get some details and maybe some ideas from the papers I published back then might be interesting to you, because I think when you hone in on, I think you're estimating a correlation, right? You could think, instead of parametric correlation, you can think of Kendall's tau as an alternative. One of my first papers is showing that for a certain bivariate distribution, the Marshall-Oakland BVE distribution, the Kendall's tau is equal to the Pearson's correlation for that distribution, which tells you something about them. But then I was looking at applications to randomized trials, which of course I deal with here all the time in industry. So if you're comparing groups, you can focus your question on a certain hypothesis of a certain statistic that you want to test between groups. And when you do that, you might find that rather than focusing on trying to estimate a likelihood or something like that, you could focus on perhaps estimating a tail parameter, like a p-value of a difference of a certain statistic, right? Under you look at your copula, what I would call my G, I was saying, well, what is the G or what is the copula that would maximize my p-value? That's the sort of thing I was looking at. So that kind of so I had success looking from that point of view.
Okay, yeah, that's interesting. I'll make sure I'll have a look.
Sure.
Well, it was very nice talking to you, Mike and Michael, and good to see you, Elif. Always.
Hi, Radu. Thank you very much for agreeing to speak in the seminars. I really appreciate your time and
Thank you for inviting me.
the great talk.